In this video, we will discuss a little bit of details about the M step or maximization step. So recall that in the previous video, we derived a variation lower bound for our marginal log likelihood. So we wanted to maximize marginal log likelihood, but instead we are going to maximize this lower bound. And on the M step, we want to maximize this lower bound with respect to theta, our parameters. And the lower bound looks like this. So it's sum with respect to the objects in the dataset, then sum with respect to the values of the latent variable t, and then some weighted logarithms of the ratios. Now we can use the property of the logarithm, that logarithm of the ratio is a difference between logarithms, and we'll get something like this. And note that the second term in this expression, it is constant with respect to theta, so it doesn't depend on theta at all. Which means that then we're concerned about maximizing this value with respect to theta, we can throw this term away and nothing will change. So we can just, ignore this and it will not change our M step. Which means that we can maximize the first term instead of the full lower bound. And the first term you can rewrite by using the following notation. It's just an expected value of the joint distribution P of x and t with respect to the variational distribution Q. So one more thing to notice here is that this function, which we are trying to maximize with respect to theta on the M step, is concave. Maybe not always, but usually you choose your P of x given t and P of t yourself. So you can choose this function to be such that the logarithm of it is a concave function, which means that it's easy to maximize. And note that expected value of the concave function is still a concave function. So, for example, in the Gaussian mixture model case, this joint probability P of x and t is Gaussian, and logarithm of Gaussian is just some linear function with respect to parameters minus. Well, you can prove that logarithm of the Gaussian is concave with respect to parameters, which means that first of all, this function has just unique global optimal. Well, at least all local maximas are the same as global maxima, and it may be really easy to maximize. And usually you can even derive the analytical expression for this M step, because this problem is so much easier than the original one in most cases. So to summarize, the expectation maximization algorithm repeats the following two steps in iterations until conversions. So first of all, the E step, where we are trying to minimize the distance between the variational distribution Q and the posterior distribution P of t given the data and the parameters. And this is the same as just setting Q to be the posterior distribution itself. And then the M step, where we're maximizing the expected value of the logarithm of the joint distribution with respect to parameters theta. So now let's say a few words about the convergence properties of this EM algorithm. It turns out that we can prove that it converges to a local maximum or maybe at least to a critical point. So to see it, let's look at the following picture. On the previous iteration, theta k, we built, which we have chosen among all the family of lower bounds, we have chosen the best lower bound at the current point, which is accurate at the current point. So on the next substep, we went to the maximum of this lower bound, of this red curve, to get theta k plus 1. So let's look how the marginal log likelihood changed after switching from theta k to theta k plus 1. So marginal log likelihood at the point theta k plus 1 is greater than or equal to the lower bound at the point theta k plus 1, just because it's lower bound. So it should always hold for any point, right? Then we can say that the value of this lower bound at the current point, at theta k plus 1, is greater than or equal to the value of the lower bound at the previous point, just because theta k plus 1 is the maximum of the lower bound with respect to theta. So it's greater than or equal to any other to the value of the lower bound at any other point, right? And finally, because we optimized, we have chosen Q to be such that the lower bound is optimal in the point theta k, then this lower bound at the point theta k just equals to the log likelihood at the point theta k. So finally, we obtained such inequality that tells us that the marginal log likelihood never decreases during an iteration of the EEM algorithm, which basically means that the EEM algorithm never make things worse. And so there are two outcomes of this observation. First of all, it's a really useful debugging tool. So if you ever see in your implementation of the EM that the marginal log likelihood decreases, then you have a bug and you have to fix it somehow. And second of all, by using this kind of considerations, you can prove that the EM algorithm always converge. It may be local maximum, it may be some other critical point, but at least it's not worse than the gradient descent in this respect. So it's always converges to some critical point.